Okay, good morning, everyone. Okay, any questions from the homework? I read your question, Jackson. Any questions from the homework? There is no difference. A vector is a list of three numbers, and sometimes we write a vector in a column format. Sometimes we write it in a row format, and sometimes we just write it like this. So we can write a vector in a row format like 1, 2, 3. We can write it as a column vector, 1, 2, 3. And sometimes people just write it like this. So a vector is nothing more than a collection of numbers, an ordered list. That's really the proper word. It's a list of numbers. It's ordered. It means 1, 2, 3, 3 to 1 are different from each other. And it doesn't matter how you write them. That's okay, this is called row vector, column vector, and just as the vector, that a list of three numbers. Now, the reason we are using this notation for vector, one of the main reasons is because we multiply a matrix by a vector. So that's one of the reasons we're using this column notation. So when you have a matrix, you multiply it by a vector. For this multiplication to make sense, this has to be written in a column format. But sometimes people tell you a row vector. It means you write it like this. It means instead of being a 3 by 1 matrix, you write it as a 1 by 3 matrix if you are a vector in R3. So that's really what it is. So there is not really much difference. It's just a ordered list of numbers. Sometimes you write them as a 1 by 3 matrix. Sometimes you write them as a 3 by 1 matrix. And sometimes, honestly, you write them in this way. To be able to multiply a vector by a matrix, we use the column notation to be able to multiply by that. So technically, no difference between them. Okay, any other question beside that? Can anyone hear? Oh, can anybody hear me? Yeah, okay, I can. Okay. I got it. Okay. All right, now questions from the homework. So Kyle, just fix your speaker then from your end. Okay, questions from the homework. Are you guys doing the homework? Please do them. Next Tuesday is your first quiz. If you don't do the homework, you're going to be very much behind. All right. So I will do three of them just to get you into the spirit before we introduce the new material. And I expect answers from you. So I'm going to look at the following problems. Okay. So I will look at this problem, number 17 in section 1.3. Okay. As I said, I expect your input, every time I ask a question. So the question is, we have a vector A1, which is the vector 1, 4, minus 2. We have A2, which is the vector minus 2, minus 3, 7. And we have a vector B, which is 4, 1, H. So section 1.3, number 17. And the question is, for what value of H, value of H is B in the plane spanned by A1 and A2. What does it mean, plane spanned by A1 and A2? Okay, I remember talking about that last time. Now I want you guys to tell me, what does it mean, the plane spanned by A1 and A2? Geometrically, what does this mean? Means. Okay, I'm expecting your answer on chat. What does it mean geometric? When they say the plane spanned by A1 and A2. Yeah, but geometric, you're right. All of your answer is correct. But what does it mean geometric? What is this plane? What? So if you are in R3 and they tell you the plane spanned by A1, A2, what's the plan that you see? Before I go back to what you guys answered, which is correct. It means which plane? In an easy word, it's the plane. You're missing something. 2 points don't form a plane. Let's be very precise. It's the plane that contain. Because 2 points form a line. So for them to form a plane, what should you add, Alison? It's contain the origin, exactly, crucial. It contains the origin and A1, A2. It means 1, 4, minus 2, minus 2, minus 3, 7. That's really what I mean by this length. It means the plane that has to contain this, and the 2 points A1 and A2. A1 is somewhere here, A2 somewhere here. And that's the plane that contains those. That's really the plane. Okay, so that's geometrically what they are talking about. And now algebraically, that's what you guys, all of you, answered correctly. B in the plane spanned by mean, is the plane spanned by those two vectors, B in the plane spanned by A1, A2, it means it's B a linear combination. So it's equivalent to mean B in the span. I introduced the word span on purpose just to keep reminding you of the word span. It means be a linear combination of A1 and A2. Okay, so just to remember the language. So we have a vector B, and the question is, this vector B that they gave you has a parameter H. So depending on the parameter, for some H, the P can reside in this plane, and for some H, the P could be outside. And the question, which H will make this vector B within the plane? So the question is, which H will make B a linear combination of C1 and A1 and A2? All right, so now the problem, we understand the concept, the problem. So the question is, find H such that the linear B2 is a linear combination of that. So now the question is, we want to find the H such that this has a solution. So that's really what the problem boils down. Which value of H make this vector equation consistent if you want? So now we set up this. I've done it several times. At this stage, I will not write the whole picture. I encourage you to write it. So for 1H, that's my B. The coefficients of C1 are going to be the entry of the vector A1. And finally, minus 2, minus 3, 7. And now we just have to ask which H make the system consistent. So I think the only way we answer those questions is by solving. Solving means row reducing immediately. That's a 0. I have to multiply by minus 4. Minus 4 times minus 2, that's a 8. 8 minus 3, it's a 5. Minus 16 plus 1, minus 15. That's a 0. And you multiply this by a 2. Minus 4 plus 7, give me a 3. And multiply this by minus 2, I will get H minus 8. Okay, what do you want me to do next? Remember, to be able to argue or to be able to ask for which H we have a solution, we have to get to the echelon form. What do you want me to do next quickly? Exactly. Nobody like this 5. We're going to actually make divided by 5, the second row, because we can. You know, the numbers are very easy. 1, 1, 0, 1, minus 3, 0, 3, H, minus 8. Still, I'm not ready. We're not in echelon form. We cannot start discussing the solution. So we have 1 here, 1 here. I need to make this into a 0. So minus 3 R2 plus R3. This is my new R3. And then I will get the following. 1 minus 2, 4, 0, 1, minus 3, and finally 0, minus 3 plus 3, it's a 0. If I multiply this by minus 3, I get a 9. I add them, h minus 8 plus 9, that's give me h plus 1. So B in the span, or B is in the plane spanned by A1, A2, if, what's the condition? Under what condition quickly? Exactly, we need a solution. This system have a solution. We cannot have a pivot in here. It means this has to be equal to 0. If h plus 1 equal to 0, it means h equal minus 1. Okay, so that's a quick, I'm picking problems, so the lecture, so you guys remember all the concepts. Okay, question number 2, I will look at it, is, please, if I move the paper fast, let me know. So now I will look at number 19, and then I will move on. Give a geometric description. So we have two vectors, V1, which is 8, 2, minus 6, and V2, which is 12, 3, minus 9. And the question is, give a geometric description. So geometric description. So it means, is this a plane? Is it R3 of the span of V1 and V2? Okay, I'm expecting answers. Celine, let me finish this and I'll go back to you, Celine, okay? All right. Give me a geometric description of the span. Josia tells me the span is a straight line. Do you agree with Josia? Yes, no, why? Yes, because. You guys have to justify everything. They are multiple of each other. Okay, so whenever you have a vector, two vectors, and you ask yourself what is their span, the first thing you do is to check, are they scalar multiple? If they are scalar multiple, it means they are on the same line through the origin. So every constant multiple of them is going to be on the same line. So we cannot jump till we ask ourselves. So the question is there a common multipliers between the component? If there is a common multiplier, it means they are scalar multiple of each other. So let us check. From here to here, you multiply by 12 over 8. It means divide by 4 by 3/2. Is this multiplier keep going? From this component to this component, you're multiplying by 3/2. From this component to that component, you're multiplying by -6 over that, which is 3/2. So this tells me that the vector V2 is 3/2 the vector V1. Absolutely scalar multiple of each other. So it means that, when you're graphing them, this is V1, V2 is 3/2. So V2 is going to be rather here. So now if I take any, and this is 0. So if I take 2V1 plus 3V2, which is what the span is, I'm going to be on the same line. So anytime I take a combination of those two vectors, I will be exactly on the same line. So this is the line. That's the geometric description through 0. It means when I say through 0, it means I mean through the origin. And you can either pick V1 or V2. It doesn't really matter. And V1. When I say V1, it means I'm talking about the tip of V1, the point V1. Okay. All right. Any question? I want to come back because your classmate had an issue with my previous computation. In the matrix of number 17, Isn't the bottom row supposed to be 0, h plus 8? I usually do stupid math, so I trust you guys. So here I have to multiply this by, okay, your problem is here. How did I get here? I multiply this by 2. 2 minus 2, 0. Correct. I multiply this by 2. Minus 4. I multiply this by 2. Sorry. Okay, thanks, silly. My apology for the previous problem. This has to be h plus 8. And this will give me h plus 17. H plus 17. H equal minus 17. So the previous problem should be h equal minus 17. Thanks, Celine. All right. So last time we started the product of a matrix times a vector. And we gave two definitions of a matrix times a vector. Who can remind me the two definitions? The main definition and then an equivalent definition. What was the main definition of a matrix times a vector? Quickly. What was the first definition? It was the linear combination of the columns of A. It's the linear combination with weight, the entries of X. And the equivalent definition, we use what we call the row column definition. And whenever I'm multiplying a matrix by a vector, I will go back and forth between them. Row column definition. So we took a simple example. So let's say 1, 2, 3, 4, 5, 6, lack of other number. If I multiply them by x1, x2, the product is either you can take x1, 1, 2, 3, plus x2, 4, 5, 6, or row column. It means x1 plus 4x2, row column, 2x1 plus 5x2, row column, 3x1 plus 6x2. And we will be going back and forth between those two notations. Okay. So suppose I ask you now the following question, which is again in your problem. So the question is, we have a matrix A, and this is, put me number 35 in your homework. So I have a matrix A is 4, 5, minus 6, and minus 3, minus 2, minus 2, and 2, and 1, 5, minus 3. And you are given that this times the following, minus 3, minus 1, 2. This is equal to minus 7, minus 3, 10. Okay, and the question is the following. This is the vector B. This is A1, A2, and A3. We write B as a linear combination of A1, A2, and A3. So the question is, we write B as linear combination of A1, A2, and A3. So what are they looking for? Quickly, what is B? What is B? So that tell you take this matrix, you multiply it by that, and you get this vector B. We write B as a linear combination. What is B? So that's A1, that's A2, that's A3. Okay, quickly, how can I write B as a linear combination without any computation or whatsoever? No. A1 plus A2 doesn't give you B. 4 minus 3 is 1. B is exactly. That's what Allison said. What's the definition? That's why I'm reminding you the definition of a matrix times a vector. What does it mean, a matrix times a vector? What's the definition of it? It's the linear combination of the columns of A where the weight are minus 3, minus 1, and 2. So if this is equal to B, it means B, that's the vector to the right, is minus 3, that's the first entry of the vector, times 4, 5, minus 6. So these are the weights that you should put on A1, A2, and A3 to get the vector B. Minus 1 times minus 3 minus 2, 2, plus 2 times 1, 5, minus 3. That's what it means. Please be very careful because you will be using this idea and I want it to become very natural to you because it's not obvious. Okay, so this matrix times is equal minus 7. It means if you use the row column definition, you get minus 7. Let's give me minus 12 plus 4, which is going to give me minus 8. Minus 8, no, sorry. That's minus 12. Minus 12 plus 3, that's going to give me a minus 9 plus 2, that's minus 7. So if I use the row column, I get that. But another interpretation of this multiplication is the linear combination of the column of A. So be very careful with that because you will be using it continuously. Any questions? All right. Okay. So last time we defined this and then we started talking about the matrix equation AX equal to B. AX equal to B. Okay, so for example, let me take again, I will use one of the problem I've assigned to start the lecture. So suppose I take the following matrix, A equal 1, 0, minus 2, which is actually number 11 in your book that I'm going to expand on it. 2, 1, minus 4, 4, 5, minus 3. And I have the vector B, which is minus 2, 2, and 9. And question number 1 is, solve AX equal to B. Okay, so let's see one more time. What does it mean to solve? Remember when I talked about it last time? As I said, when you guys first learn multiplication, they teach you how to solve 2 times x equal to 3 and x equal 3 half. And you can think of it at the same way. We introduced the notion of multiplication of a matrix times a vector, and now we're solving a times x equal to b. So that's really, basically, we're generalizing a lot of ideas you have seen. So what does it mean to solve this? Means we go back to what does this mean? 9, 1, 0, minus 2, 2, 1, minus 4, 4, 5, minus 3. X, whether they tell me or not, I should know that X should have 3 entries because I have 3 columns here. They can tell me sometimes how many or they don't have to because we're supposed to know. So solving this is equivalent to solve the following. I can use either definition to multiply. So the row column is easy for computation. It means x1 plus 2x2 plus 4x3. And this gives me x1 plus 5x2 minus 2x1 minus 4x2 minus 3x3. This is equal minus 2 to 9. Okay, so it means I'm solving the following system. Equal to and minus 2x1 minus 4x2 minus 3x3 equal to 9. So solving this matrix equation, it means solving the system, okay? Which means solving the system where the augmented matrix is 1, 2, 4, minus 2, 0, 1, 5, 2. So that's the augmented. Minus 2, minus 4, minus 3, and 9. Okay, so solving the vector equation AX equal to B really boils down to solve the system of equation. It means the system where the augmented matrix is A here and B here. That's what it means solving. And the solution, we write it as a vector because that's what we're looking after. We're looking after the vector X. So now we solved the system. I think by now I don't solve system anymore. You guys give me the augmented, the echelon form, or I have it. So now we solve this. You guys do the work. I won't do it in class unless I have to. 0, 0, 1. After you do everything, 0, minus 3, and 1. It means if we solve this, so this will give me, the first row tells me x1 is 0. The second would tell me x2 is minus 3. And the last one would tell me x1 is 1. So it means the solution is x equal, I use vectors to solution because I'm solving A times x. It means I expect the solution to be a column vector, 0, minus 3, and 1. So we're using vectors to represent a solution because I'm solving A times x equal to B. My x is a vector in here. Okay. Now I'm going to add the following. Question number B. Question number B is the following. Write the vector B, it means minus 2, 9, as a linear combination of the columns of A. Okay, so let me put what the picture in your mind. That's what I want. I solved AX equal to B. I got this as a solution. That was the solution. And now my question is, write B as a linear combination of the column of A. So these are the column of A. I want you to write B as their linear combination. Can anybody answer this question? We solved. This is the solution to that. If I take A multiplied by this vector, I should get B. So my question is, write B as a linear combination of the columns of A. Anybody? B is minus 3A2 plus A3. Anybody agree with your classmate? Anybody agree with Allison? Please look at what she said. Okay, absolutely. Let me comment on what Allison said because I want this to be relatively clear. I mean, definitely clear. So write B as a linear combination. Let us see what we did in part A. In part A, what I showed you by solving the system is the following. So from A, we saw that if you take the matrix A, so this is the solution vector. And I get minus 2, 2, 9. So if I take 1, 0, minus 2, 2, 1, minus 4, 4, 5, 3, that's my A. And when I solved it, that's the solution vector, I get the vector B. That's what we did. So it's literally, if you guys multiply, use the row column, 0, -6, +4, you get -2. Row column, you get this vector. Now, I want you to use that to show that this vector is a linear combination. So now if we use the definition, of the product of matrix times a vector times a vector. What does this tells me? What's the product? This tells me if you take 0 times the first one minus 3 times 2, 1 minus 4 plus 4, 5, 3. So 0 times the first vector minus 3 times that vector plus 1 times this vector. That's the linear combination. This would give me the vector B. That's the definition. It means the vector B is -3, the first column, plus the last column. So B is a linear combination. So when we solve AX equal to B, we actually do two things. We find the vector that you multiply it by A, you get B. Second, we find the weight that we have to put on A1, A2, and A3 to give me the vector B. So let's write this out a little bit so we can keep that in mind. So let us connect the dots. Solving the matrix equation, AX equal to B, because that's the new way you're going to see a system written. That's why we emphasize this. Solving AX equal to B, basically equivalent to solve the system where the augmented matrix AB. So whenever you have to solve that, that means that you have to solve the system. Now, if the system is consistent, one interpretation of the solution is the entries of the solution vector, the one we found a minute ago, are the weight that gives B as a linear combination of the column of A. So when you solve this equation and you get a solution, the entries are the weight that you put on the column to get the vector B. In particular, the vector B is in the span of the column of A. So if you solve X equal to B, you get the weight that gives you B as a linear combination. So it means that the vector B is actually in the span of the column of A. The difficulty here is to be able to see this piece. It's not always clear for the student because it's weird that we have two definitions for the product. Now, the last thing from this section we're going to do is the following idea. Very simple, but I'm going to put something in front of you. Okay. Let us consider the following system. So my question is, find a matrix A and a vector B such that solving the matrix equation AX equal to B is equivalent to solve the above system. The point is, as you move forward in your studying, a lot of time, instead of giving you a system written this way, you will be given something of the form AX equal to B. And our job now is to understand that solving the system is the same as solving AX equal to B. So what is the matrix A and what is the vector B? So the matrix A is nothing more than the coefficient of the system. So A would be 1, 2, 1, 1, that's A. And the coefficient here, so A will be -1, 3, 0. So A is the coefficient matrix. X is the vector whose entries are the unknown. We have 4 unknown, x1, x2, x3, x4. And B is the vector whose entries are the constant term. Okay, so solving, if I consider the system, solving the system is basically solving this AX equal to B. So very frequently, instead of giving you the system, you will be given solve AX equal to B and vice versa. Solving this system is solving that matrix equation. Solving this matrix equation is solving this system. So we'll go back and forth between those two notations. Part 2 is the same ideas, but we're going to move a little bit forward. So we're going to represent the solution in a slightly different way. So section 1.5, solution set of linear system. First definition. If you have a system of linear equation, the system is called homogeneous if it can be written in the form AX equal to 0. So a homogeneous system is a system where the right side is all bunch of zeros. That's what a homogeneous system is. So example of a homogeneous system is, this is a homogeneous system. Everything to the right is 0. So x1 plus x2 equal to that. This is equal to 0, and this is equal to 0. So in matrix format, this is equivalent to say the following. That's how we write in matrix format. This is my A, which is the coefficient matrix. This is my vector X, and my vector B is the 0 vector. So in matrix format, that's how we write this homogeneous system. Now, a question addressed to you. Does a homogeneous system is always consistent? Is a homogeneous system always consistent? Do we always have a solution for the homogeneous system? Yes or no? Yes, give me a solution. Quickly. If there is a 0, 0, 0. So every homogeneous system are always consistent. Okay, so 0, 0, 0 is a solution. Immediately. So we don't have inconsistency issue when we have a homogeneous system. So this means that the following happens. Since it is always consistent, and as we said earlier in the semester, a linear system cannot have two solutions, either no solution, unique, or infinite. So whenever we have a homogeneous system, we're going to have the following scenario. Either we're going to have a unique solution, which would be the 0 solution, or we will have infinite solution because we don't have inconsistency. So whenever we have homogeneous, the question will be, is it unique or infinite? Finally, the word solution set. Solution set means if the system have infinitely many solutions, it means the solution set is all the solution of the system. So whenever we have infinite, they talk about solution set, it means they are talking about all the solution, not one or two, all of them. That's what they mean by the word solution set. Today, what we're going to do is we're going to solve solution system, a homogeneous system, and we're going to write the solution in a specific format called parametric vector form. So what I'm going to do is solve a homogeneous system the way we've always solved them, but the only new thing is we're going to represent them in a slightly different way. So here we are. The question is solve the following system. Oh, first of all, let's consider the following homogeneous system. The one I just put on the board, so x1 plus x2 minus 3x3 equal to 0, and 2x1 plus x2 minus 4x3 equal to 0, and finally x1 plus 2x2 minus 5x3 equal to 0. Let us consider the system. Question number 1 is solve the system. Okay. So solving is what we solve. I have to move to a pencil because I do a mistake here. 1, 1, minus 3, 0, 2, 1, minus 4, 0, and 1, 2, minus 5, 0. Okay, so let us solve this system. Actually, I'm going to give you the solution. So I don't have to do all the work. So this is going to be equivalent 1, 0, minus 1. You guys make sure you can do row operation. 0, 1, minus 2, 0, and 0, 0, 0, 0. We expect a bunch of 0 at the end because any row operation will not affect those zeros. So this is my solution, 1, 1. So let's remember how we write the solution. It means x1, before I write this, x3, 3, x1, x2 are the basic variable. Okay, should remember that. So now let us write the system that corresponds to that. So the first row read x1 minus x3 equal to 0. The second read x2 minus 2x3 equal to 0. And the last one reads 0, 0. And as you said, solving the solution. So what's going to be the general solution? Solving, it means express everything in terms of the free variable. So x3 is free. The second equation gave me x2. It's 2x3, everything I'm doing now. If you know, you should know at least. And x1 equal to x3. Okay, so that's what we have so far. Question number 2 is what's a little bit new in this section is question number B is the following. Write the solution. Write the solution in parametric vector form. In parametric, to write the solution in parametric vector form. Okay, as I said, that's the only thing new in here. What do they mean by that? It means the following. We introduce a parameter, call it t. So we set the free variable equal to a parameter that we called t. And then we're using this new notation, x1 will become t. So I'm substituting this here. x2 is 2t and x3 equal to t. Okay. And now I'm going to use vector notation to represent the solution. And we do it as follows. So if x is a solution, if the vector x is a solution, then we're going to write x in the following way. X is, so the entries x1, x2, x3 is equal to, x1 is t, x2 is 2t, x3 is t. Means this is equal to. So that's how we are going to write. We will factor out the t. The t is a parameter, is a constant. It means if x is a solution, then x could be written as t times 1, 2, 1, where t can take any value. Okay. This representation, this is called, this representation here, this is called the parametric vector form of the solution. Okay, so that's really the way we're going to represent the solution. So this form is called the parametric vector form of the solution. Now let us analyze the solution because it's an interesting way of viewing it. You're going to view the solution geometrically and we are going to view the solution algebraically. First, so this tells me that every solution vector is a scalar times the vector 1, 2, 1. So how can we visualize the solution? So let us visualize the solution. So geometrically, who can visualize the solution? I want you to stare at the way we wrote it and see if you guys can interact with it. Every solution, the entries is a scalar multiple of 1 to 1. How can we visualize this? Look at it a little bit, analyze it. A plane. Think a little bit more. I'll give you a minute to interact with it. It's not hard. Every solution is a scalar multiple of the vector 1 to 1. Okay, anybody else? It's a line. Let us understand why it is a line, not a plane. Why it is a line. So suppose this is in R3, for example. And let me draw the vector 1 to 1. 1, 2, from here and 1. So it is right here. So this is the vector. I'm going to go up a little bit more. So this is 1 to 1. Okay, so let us analyze the solution. T can be any parameter. If T is 0, it means that's the 0 solution. If T is 1, that's a solution. What is every other solution? Every other solution is a scalar multiple of 1 to 1. It means every other solution is basically, if so this is T equal to 1, give me that. If I take T equal to 2, it means 2 times 1 to 1. So this is, I get this. T equal to 2. T equal to 3, okay, I get this solution right here. T equal minus 1, I'm getting a solution down here. T equal minus 2, I'm getting the solution down here. So every solution is, the solution basically is the line that go through the origin and the point 1 to 1. So geometrically, the solution is a line through the origin and 1 to 1. It means through the point 0, 0, 0 and the point 1 to 1. Does this make sense that the solution is a line? Does it make sense to you that yes, because initially what were we solving? Let's see what we were solving. We were solving the system of 3 equations of 3 unknowns. Geometrically, every solution for those who had calculus 3 is a plane, and a plane. So what we are really finding is the intersection of those 3 planes. That's really what the solution should be. And the solution here, this line, is basically the intersection of the 3 planes. So we're really getting a line, and it makes sense geometrically because that's what we are doing. So this is called the parametric vector representation. It's really help us to understand fully what the solution is. So every solution is a scalar multiple of this vector. That's really what it is. Now, algebraically, what's the solution? Or the solution set is basically the span of the vector 1 to 1. That's what the solution set is, the span of this vector, meaning every linear combination of this vector A linear combination of one vector means every scalar multiple of the vector. So we were able to see the solution in two different ways. Geometrically is a line, and algebraically is the span of one vector. And we know that 0 is always a vector in the span. Please ask questions and try to be with me as much as you can. So question number 2 is, problem number 2 is the following. I'm going to do the same thing along the same line, but system with more than 3 unknowns, and learn how to write the solution parametrically. So now let me consider the following system. Okay, sorry. X1 plus 3x2 plus 5x3 plus 4x4 equal to 0. X1 plus 2x2 plus 2x3 plus x4 equal to 0. So that's again a homogeneous system. And I would like to write this using matrix form. So this is, I'm going to rewrite it just to keep reminding you how to rewrite. That's the 0, 0 vector. The A is the coefficient matrix. 1, 2, 2, 1. And x1, x2, x3, x4. So solving this system is the same thing as being told solve this system. So these are very, very much the same thing. We're doing the same operation basically. That's the 0 vector. All right, so let us solve. As I did before, step 1, I'm going to solve. Step 2, I'm going to write it in parametric vector form. So my question, actually, I'm going to write the following. Solve the system and write in parametric vector form. Okay. So let us solve the system. 0 and 1, 2, 2, 1, 0. All right, before I go on, how many first, I know that the system is consistent. What's the minimum number of free variable you should get? What's the minimum number? 2. 2 is the minimum number. So we should get at least 2 free variables. We might get 3, I don't know, but at least we should get 2 free variables. So we will so 1, 3, 5, 4, 0. Minus 1 plus 1 is 0. Minus 3 plus 2, it's a minus 1. Minus 5 plus 2, minus 3. Please watch my computation. I do mistake at this stage. Minus 4 plus 1, that's a minus 3. And this is a 0. Okay, I will go to how do you know there are 2 free variables? Good question. How many rows do we have? I said at least 2. How many rows? Okay, it means how many leading entries we can have at most. At most, how many leading entries we can have? Also 2. So it means at most, how many basic variable we can have. If you have, remember, the basic are correspond to the column with leading. If at most we can have 2 basics. So at most we can have 2 basics because we can have 2 leading. It means the rest will have to be free. Haley, does it make sense? Yep, okay, very good. So now what I would like to do, I would like to go to the reduced echelon form just so I won't have to do back substitution. But I have a minus 1 here. I'm going to turn this into a 1. So I'm going to cheat. I'm going to put 2 here just to make this one. So I did two operations, you guys don't. And finally, I want to go to the reduced echelon form. So I have to take the second row, multiply it by 2, add it to the first, and this would be my first row. Okay, so I'm not touching this one. Sorry, minus 3 R2, my apology. Minus 3 plus 3 is a 0. Minus 3, that's going to give me minus 9. Minus 9 plus 5, that's a minus 4. And that's what give me minus 9. Minus 9 plus 4, that's give me a minus 5. Okay. All right, that's a 1, my leading. And this is a leading. That's in reduced echelon form. I cannot go any further. All right, so now let us analyze. Basic and free. So the basic variables are the ones that correspond to the column with leading entry. Basic, x1, x2. Free are x3 and x4. Okay, so these are the basic and these are the free variables. And now let us write the system that correspond to the augmented matrix, to the echelon form. The first read x1 minus 4 x3 minus 5 x4 equals 0. And the second row read x2 plus 3x3 plus 3x4 equal to 0. Okay. And now we're going to write the solution. We're not treating the vector form yet, we're just writing the solution. So the general solution. Remember, the general solution, all the basic has to be expressed in terms of the free variable. x3, x4. x4 is free. That's free. x2. I'm going to pick it up from here. It's going to be minus 3x3 minus 3x4. x1, I use the first equation. 4x3 plus 5x4. Okay, so far everything here is something we have done before. And now parametric vector form. In the parametric vector form, how do we write it? I have two free variables. And remember, the variable don't have to take the same value. I can take x3, 5, x4, 0. So they really two different parameters. So in parametric vector form, we would do the following. We introduce two parameters, one for every variable. So we're going to set x3 equal s, two parameter, x4 equal to t. And then, so this will give me that. x1 become for s plus 5t. x2 become minus 3s. x3 is s, and x4 is t. And now the last step, which is the new step, I want to rewrite this using vector form. So let's see how do we write it. So suppose x is a solution. It means x have x1, x2, x3, x4. So this is equal to, for s plus 5t minus 3s minus 3t s and t. So far I'm not doing anything, I'm just rewriting the solution. Now I'm going to write the vector form. How we rewrite this using vector form, and watch carefully how we're going to rewrite it. In the previous problem, I had one free variable t, and I was able to factor it out. So I can show you that every solution is a combination of the one vector. Here I have two parameters, so I cannot really factor anything. So the way we are going to do it is, we're going to basically write it as sum of two vectors as follows. I will do it slow the first time. Next time, you got to do it faster. Everything coefficient of S, I will put it in one column. S and the 0, and everything in T in the other one. Okay. And then the last step would be, in this stage, I can factor out the S. Give me S times 4 minus 3, 1, 0, means X equal, plus T times 5 minus 3, 0, 1. This is what we call the parametric vector form of the solution. So this is called the parametric vector form of the solution. So this tells me it's a very good way to represent the solution. It means every solution is basically, to get a solution, first, to get a particular solution, the only thing you have to do is give the parameter S and T value. So if I take S to be 0, and T is 1, 5 minus 3, 0, 1 is a solution. If I take T0, S is 1, 4 minus 3, 1, 0 is a solution. So there are infinitely many solutions. And algebraically, we can view every solution as a linear combination of this vector and that vector. So if I call this vectors V1, I call this vector V2, then I can say that the solution is actually the span of those two vectors. Because we can totally, basically, in a way, understand better the solution. Every solution is a combination of those two vectors. It means once I know those two solution vectors, everything else is a combination of them. So that's what we really mean by parametric vector form. And sometimes people say that this span is a plane. I mean, we don't use this language in this course, but sometimes they say this is a plane in R4. R4 because we have 4 components. The reason they use the word plane because it takes two vectors to span a plane in R3. So sometimes they actually generalize and they call this a plane in R4 because the solution is a combination of two vectors. Question as I move on, please. Okay. Now, part 2 is, what if I don't have a homogeneous system? I have a non-homogeneous system. Now, we have an issue. It means the system could be consistent or inconsistent. But let us assume I have a non-homogeneous system and it is consistent. How can I write the solution using parametric vector form? So the last example I will do is the following. So non-homogeneous system. Let us consider the following system. And the question is, that's my system. Equal -1. So it's not homogeneous anymore. 2x1 plus x2 equal 4. And x1 plus 2x3 equal -7. So that's a non-homogeneous because I don't have all zeros in the right term. And the question is solve and write in parametric vector form. All right, solve is solved. So we're going to take 1, 1, minus 3, minus 1, 1, 2, minus 5, and minus 7. Okay, and we will do exactly what we've been doing. We're going to reduce. And when we reduce, we get the following. 1, 0, minus 1, 5, 0, 1, minus 2, minus 6, and 0, 0, 0, 0. So that's the reduced echelon form, actually. So now this is my leading. This is my leading. And so as I did before, x1, x2, those are the basic, and the free is x3. So now let us write the system that corresponds to the augmented. x1 minus x3 equal to 5, x2 minus 2x3 equal to minus 6. So now the general solution, x1 is 5 plus x3. Because I went to the reduced echelon form, I did not have to do back substitution. x2 is minus 6 plus 2x3, and x3 is a free variable. Now I'm going to do the parametric representation. So we will set x3 equal to t. And then x1 would be 5 plus t. x2 will be minus 6 plus 2t. x3 will be t. So how will we write this in parametric vector form? So the vector x, the solution vector is 5 plus t minus 6 plus 2t and t. And I'm going to split this. Basically, the idea is to split this in a way we can better understand it. So how can I split this? Okay, as I did before, I cannot really take t out. So we're going to basically split it into two vectors, or decompose it if you want. In one column, I'm going to have everything that has nothing to do with t. And in the second column, I will have everything multiplied by t. So now we rewrite this as 5 minus 6, 0, plus t times 1, 2, 1. And in this case, that's the parametric vector representation. So it's not, it's because 0, 0 is not a solution, so it's not the span of the vector 1 to 1, is the vector 5 minus 0 plus t times 1, 0, 1 to 1. So that's the vector, parametric vector representation. So when we have a non-homogeneous system, we definitely have a different approach. Okay, now I want you to look at this vector. And can anybody a little bit see it geometrically? What this could represent? So every solution is, let me write it. So every solution, you can think of it as, let me write it this way. Okay, think a bit about it. How can we visualize this? Anybody? Similarly to y equal mx plus b. Yeah. So remember we are in R3. Okay. Line passing through that point correctly, Pedro. Okay, let us, exactly. Now you guys are getting it. All right. Suppose I take t equal to 0. If t equal to 0, this is a solution. So let us assume that this is, it should somewhere here, this is 5 minus 6, 0. So that's a solution. If t is equal to 1, so t equal to 0, that's a solution. So t equal to 1, it means what are we going to have? I'm going to draw right here the vector 1 to 1. So if I put t equal to 1, I get the following. 1 to 1, the vector 1 to 1, plus 5 minus 6, 0. It means graphically I'll get the following. This is 1 to 1. You're adding to it 5 minus 0. T equal to 1. And then t equal to 2. It means you go a little bit this way, and then you add the vector 5 minus 0. T equal to 3. You go this way and you add this vector. So all the solutions are going to be exactly on this line. So it means the solution is going to be geometrically, the solution is the line that go through this point. So that's going to be the point, the line that go through. Through the point. 5 minus 6, 0. So that's going to be the point on the line. It doesn't go through the origin. And in the direction, is the line in the direction of the vector 1 to 1. What does it mean in the direction of the vector 1 to 1? It means it's parallel to the vector 1 to 1. So the solution will be the line. It goes through this point, and it moved in the direction of the vector 1 to 1, meaning parallel to the vector 1 to 1. So that would be the solution. Again, it makes sense. We're talking about 3 planes. The 3 planes do not go through the origin. So we don't expect the origin to be on it, but so this line will go through this point, 5 minus 6, 0, because we get it when t equal to 0, and it moves parallel to this line. So every vector is minus 5, 0, then you add 1 to 1. Sorry, 1 to 1, you add 5 minus 6, 0. 2 times 1 to 1, you add the same vector. 2 times, 3 times, you add the same vector. It means like you're taking this vector and you're translating it. So it goes through the point 5 minus 6, 0. All right, so we stop, of course, at this stage. Please make sure you do the homework. And I have office hours. If you have any questions, please make sure you do them. If everything goes according to what I'm hoping they will go, I should be in school on next Tuesday for your first quiz. Okay, so please, as I said, do your homework and I'll see you on Thursday. Any questions? No. My quizzes are, everything is closed. No open books, no. No open books, and there will be no calculators because you have to do the echelon 4. And with echelon 4, calculators can give you everything. I cannot even afford that. So there will be no calculators, but the numbers will be very easy, and definitely no notes. Any other question? Okay. Have a good rest of the day and see you on Thursday. Bye-bye.